So we've got a question here that deals with a little trick for finding the number of prime factors or the number of factors, period, that a number has based on its prime factors. And to illustrate this trick, which I'm outlining at the bottom right-hand corner here, I'm going to use an example which doesn't follow the exact rule that we've been given in this question, but has a similar principle behind it. So the example is going to be the number 12. And if we factor the number 12, we see it has factors of 1 and 12, 2 and 6, and 3 and 4. So it has a total of 6 factors, kind of like the situation we have in this question stem. And another way we could have quickly figured out how many factors 12 has, including the number 1 and the number 12 itself, would have been to take the prime factorization of 12, which is 2 squared times 3 to the 1. So it's 4 times 3. Take that prime factorization and then take each of the exponents from the prime factorization. And if you have more than 2 factors, 2 prime factors, you would take as many prime factors, exponents as you have. But we're going to just take these 2 because this is all we've got. You take those prime factors, you add 1 to each of them, and you multiply them together. And what we get here is 3 times 2, which equals 6. And this is just a trick. This is just something to put on a note card and memorize. It's a quick way to find the number of factors that a number has based on its prime factorization. So if we know that k has 6 total positive factors, including 1 and the number itself, and we know that k can be represented as 3 to the k times 7 to the y, 3 to the x times 7 to the y, because we're told that k has factors of 3 and 7. And we also know that x and y cannot equal 0 because they wouldn't tell us, yeah, we have a factor of 7 when it's 7 to the 0, which just equals 1. So we assume that x and y both have to be positive numbers. Neither of them, they're not fooling us and making one of them 0. Then that means either x is equal to 2 and y is equal to 1, or x is equal to 1 and y is equal to 2. Because if we look at the trick that I outlined down here, if we know the total number of factors is 6, and x plus 1 times y plus 1, which are the exponents on our prime factors, give us the total number of unique factors, then x plus 1 times y plus 1 has to equal 6. And these have to be whole numbers, because we're dealing with a positive integer for k, and that means that we have a positive whole number up here, which would only make sense if these two things multiplied to give a whole number. So for example, having both of them as whole numbers would be a way to guarantee that, especially if we have exactly 6 factors. So if we know that the prime factors are 3 and 7, then we know that either x is 2 and y is 1, or x is 1 and y is 2. Looking at statement 1, it says 3 to the 2 is a factor of k. Well, that means that the x has to be 2, and that means the y has to be 1. And if I know that the factors are 3 to the 2 times 7 to the 1, then I know that this is 9 times 7, which is equal to 63. So statement 1 is definitely sufficient. Statement 1, sufficient. Statement 2 says that 7 squared is not a factor of k, but we know 7 is a factor of k. And so that must mean that the y is equal to 1, because the only alternative option given this situation was for y to equal 2, but we know 7 squared is not a factor of this number, so it must be 7 to the 1. So that tells us that statement 2 also gives us the same information as statement 1, and it's also sufficient. We know that it's 7 to the 1, and then we must have 3 to the 2 paired with it, given the info they gave us in the question stem. So there's a little bit of a trick to this, which I don't typically like to focus on tricks, but this is a good, useful one to put on a note card. I think that it's probably difficult to solve this if you didn't know that in advance.